Okay, welcome everyone. I'm Kannan Muthukkaruppan, co-founder at Yugabyte, and it's my pleasure to welcome you all to another episode of our YugabyteDB Friday Tech Talk series. I have with me Kai Franz, an engineer on the database team, and he's here with an interesting topic. I'll hand it over to him to introduce himself as well as the topic for today.
Hi, everyone. I'm Kai. I'm a software engineer here on the database team. And today I'm going to be talking about how to eliminate redundant indexes in your database to get better performance. So just to go over the agenda, first I'm going to talk about the benefits of why you want to build an index in your database. And then I'll go over the performance drawbacks of having too many indexes. And then I'll talk about when you can tell that an index is redundant. And then finally, at the end, I'll do a demo of how to automatically detect and remove redundant indexes in your database. So let's say that you have a query, a simple query like this one, select A from T where B equals 2. In order to speed up this query, you want to create an index on column B here. And that's going to make the runtime of your query go from O of n to O of log n. So that's a pretty simple example of when you would want to create an index. Flip side of that is that every index that you create has these hidden costs that you might not notice immediately. So one of them is that each index takes up additional space on disk and in memory because that index is essentially a copy of all of the key columns and the primary keys of that table. And the other drawback is that every time there's a write to the table, we have to update every index on that table. So there's a performance penalty on writes. And to make this even worse on a distributed database, this write penalty can be even higher because your indexes might be distributed across different nodes. So when you do a write, you might have to go out to a bunch of different nodes to update those indexes. So for these reasons, we want to have all the necessary indexes, but we really want to minimize the number of unnecessary indexes in the database to maximize efficiency. So first, since we talked about the performance characteristics of indexes, how do secondary indexes actually work? So to give an example, let's say that you have a simple base table, users, and it has these 3 columns, ID, which is the primary key, and then email and first name. And then you create an index on this table on the email column. So what this index is going to look like is it's essentially a table that's sorted by the email column. And then over here, we have the primary key for each email. So when you want to do a lookup on this index, you search for the email and then get the primary key for that row. And then you can go back to the base table and then look up that primary key and get the rest of the columns.
Yeah, so it's worth calling out that while to the user of the database, the table and the index look like 2 different constructs. Underneath the covers, they are both stored like tables. And it's just that the table that you see on the left is sorted by the primary key of the table, whereas the table on the right is sorted by the columns you have selected in the index. In this case, it's the email address, right? But both of these can grow massive sizes. They get sharded, distributed, replicated, right? So at the lower levels of the system, these two are very similar structures, and just their sort order is different.
Yeah, exactly. So let's say that we want to do an insert onto the users table now, and we have the secondary index. So what that's going to look like is we have to do an insert into the base table, and we just add it to the end here since the primary key, let's say that's a serial primary key. And then when we do an insert into the secondary index, we have to search for the right spot in this table since it's sorted in order of email, and then we insert it there. So as you can see, every time you insert a row or update a row into a table, every index also has to be updated to keep it in sync with the main table. Okay, so now we talked about the performance penalties of creating secondary indexes. So when is a secondary index not necessary? So let's say we already have this existing composite index A, B on columns A, B, and C. If we already have this index, then any index on any prefix of these columns is going to be redundant. So an index on A and B, or A, B, and C are all going to be redundant, and those indexes are not going to provide us any benefit over just having this index on A, B, and C. So to explain why this is, let's look at an example. So we have this index, to keep the same example, we have this index on A, B, and C, and let's say that we have a query, select C from T where A equals 2. So this query only provides a value for A, but I'm going to show that we can still use this index on A, B, and C to answer this query. And the way that we do this is we take advantage of how this index works. So the index is essentially just all the rows sorted in order of the keys of the index. So it's sorted on A first, and then B, and then C. So what that means is even though we only have a value for A, we can just seek to the beginning of the section where A equals 2, and then read these values sequentially until we hit the end of the section A is no longer equal to 2. And we can very efficiently read all the values where A equals 2. In fact, just as efficiently as if we only had an index on only the A column. So when should you create indexes then? One common idea is that you just want to create an index on all the columns in the where clause for every query that you have. So let's say you have select from T where B equals something and C equals something, and that's one of your queries. Then you would want to create an index on B and C. But then if you have another query where you have select from T where B equals something, then that maybe you would see that and you would want to create another index on just B. But in this case, you have to be careful because, as we discussed, the second index is redundant since B is a prefix of BC. So you actually don't need the second index. You can get by with just this first index. So now I'm going to go through some examples of redundant indexes using different types of indexes that you might see. So the first one I'm going to go over are unique indexes. So a unique index is the same thing as a regular index, but it comes with an additional constraint that all the keys in the index have to be unique. So to give an example, let's say that we have the same table as before, this users table, and you create a unique index on the email column. So what this means essentially is that this index enforces the constraint that there can only be one of each email in the table. So now let's say that you have this table and you want to insert another user with the email brandon@foo.com. And note that we already have someone with that exact email already. If you try to do that, then the unique index is going to throw an error saying that your duplicate key value violates the unique constraint, and it won't let you do this insert. So let's look at when a unique index can make your index redundant. So if you have two indexes on the same columns, A, B, but one of them is unique, that actually means that the non-unique index is redundant, because the unique index has a stronger guarantee than the regular index, and you don't need the regular index if you already have a unique index on the same columns. So the next type of index I'm going to talk about are indexes with include columns. So as an example, let's say you have this index on users, first name and last name, and then you create an index on first name include last name. And what this means is that your key for the index is just the first name, but we also include in the index the last name. So the index isn't sorted on last name at all, but the last name is included in the index, so that when you want to do a lookup on this index and you don't want to have to get the primary key and then go back to the main table to get the last name, you can just read the last name directly from the index. However, you don't get the benefit of having the index sorted in order of first name and last name. So this means that a regular index gives you a stronger guarantee than an index with include columns, assuming that the columns are the same. And that's because let's say that you have a lookup and you're given the first and last name, you can efficiently answer that query on a regular index, but on an include index, you would have to search through all of the values with that first name in order to find the right last name.
And but by the way, this way of doing the include on the index is also sometimes called a covering index. You are essentially adding additional columns like last name. And like Kai said, the reason you would do so is to avoid going to the main table if that's a frequent lookup through the index. But when you compare these two choices, the left one, like Kai said, is a stronger guarantee. But there might be other cases. For example, what if you, in addition to wanting to often look up the last name, what if you also wanted the property that the first name is unique? In that case, the partial index, like the covering index on the right might be a better choice, because you can still say create unique index on first name and include last name. So there are subtleties that you have to be careful in deciding when an index is redundant or not. But for the example Kai is showing, yeah, definitely you could just go with the index on the left rather than the right.
Right. So as Kannan said, that there are some subtleties in this case, but in general, if you have these two indexes, one on A and B and one on A includes B, then you would generally want to keep the AB index and get rid of the A includes B index. So another type of index that you can use in Postgres or in Yugabyte are partial indexes. So a partial index allows you to index only the rows in a table that satisfy a certain predicate. So let's look at an example. Here we have an index on users, first name, last name, same as the previous example. And then we have a partial index on first name, last name, with the predicate first name is equal to Alice. So the difference between these two indexes, they're both sorted in order of first name and last name, but this index only has a subset of the rows of this one. So you can see, for example, all the rows with Bob as the first name are gone in this index. So the partial index is going to be just as fast as the regular index if your first name is Alice. But if your first name is Bob, the partial index is going to be completely useless, because it's not going to have any of the rows that you're looking for there, and you'll have to look at a different index. So again, there's some subtleties here, but in the general case, if you have these two indexes that are keyed on the same rows and one has a predicate, you want to keep the index that doesn't have the predicate because it contains a superset of the rows of the index with the predicate, and therefore it's more useful. And then the last thing I'm going to talk about are expression indexes. So so let's say that you have a table called events, and one of the columns is an event timestamp. And one common operation that you're going to do on this table is to look up events by day. So you don't care about the hours or the minutes or the seconds, you just care about the day. In that case, you can create an index on the truncated timestamp of that row. And the way that you do that is you create an expression index. So you can see that this index, instead of just being on the event timestamp, it's on an expression which takes the event timestamp as input. And with respect to redundancy, the rules are pretty much the same for expression indexes. It's if an expression index is a prefix of another index, then you know that it's redundant. So that applies to expression indexes as well as regular indexes. Okay, so now I'm gonna do a demo on automatic redundant index detection. For this step.
Yeah, I think maybe I think one thing it's worth calling out at this point is a lot of the examples that we showed, while it looks fairly obvious and simple in practice, we do see this commonly in many deployments, right? We work with users and people that are using databases, and to some extent, it's not specific to YugabyteDB. Like with many databases, sometimes people maybe just misinterpret, like, and almost I would say it's like defensive programming. You already have an index on A comma B, but they also create an index on A. So the examples look fairly simple, but that's why we started looking at, like, how can we make this easier to detect rather than manually inspecting this. And yeah, Kai, I think you can continue.
Yeah, so we wanted to make this easier to detect. So what we made is a simple script that you can run and on your database, and it will tell you which indexes that you have that are redundant. And this script is still a work in progress. It might have a few bugs in it, but if you want to try it out right now, you're welcome to test it out. So the script is at this URL or at this QR code. If you want to check it out right now, I'm gonna go to this link so that we can just quickly take a look at it. So just to briefly give an overview of the script, I'm not going to go into too many details into what it's doing, but essentially this is a SQL script that grabs all of the index metadata from your database from the Postgres catalog tables, and then it looks at essentially, do you have one index that's a prefix of another index, and it takes into account the things that I mentioned earlier, so uniqueness, partial indexes, things like that.
And perhaps worth calling out that essentially we are building this into the product itself as a performance advisor. So that's very much an active project where the system will automatically help identify and call out indexes that can potentially be dropped because they are redundant.
Yeah. So we are going to incorporate this into the troubleshooting advisor. So this will be part of the product, but we just have this script too that you can run if you want.
This is like a preview version of the script.
Yeah, exactly. Okay, so now let's get into our demo. First, I'm gonna just go over. So this is what our demo is gonna look like. We have this table users, and you have the user ID primary key, and then you have a bunch of columns for user data. Some of them are varchar and text, some of them are timestamps. And then we're going to create a bunch of indexes on this table, and some of them are going to be redundant. So the first two indexes are pretty simple. You have one on first name, last name, and then you have one on first name. And as we discussed, this first name one is going to be redundant. The second pair of indexes is going to be two indexes on the updated at timestamp column, but truncated to the day. So same thing again. This first one is going to be redundant, or this first one has the user ID. So the second one that's just on the timestamp column is going to be redundant. And then the third one is two indexes on the email column. One of them is unique, and the other one is not unique. So the not unique one is redundant because it provides a stronger guarantee. The fourth set are going to be two indexes on the same column, but one is ascending and one is hash. And I didn't talk about this earlier, but the ascending index actually provides stronger guarantee than the hash index because the ascending index is sorted in order of last name, but the hash index doesn't provide that guarantee. So the ascending index is more useful for things like range queries, whereas the hash index doesn't let you efficiently answer those queries. So in this case, we would want to get rid of the hash index and keep the ascending index. And then the last example here is going to be a set of partial indexes. So one index on the phone number column and the other index on the phone number column where phone number is not null. And this one's kind of a complicated example because in practice, it's possible that you want to keep this partial index instead of the regular index. So that's why I would say you always want to double check when you have redundant indexes to make sure that you don't actually want to keep the index that you're about to drop. Okay, so let's look at the database. So I have this table and indexes all loaded in. So let me just make sure that that's all there. And then first, what I want to do is I have a query that just does a simple insert into the users table. So this is just to simulate a regular like write query. And then I'm going to run this query right now. So what we see is right now the insert query is doing 11 write requests under the hood. And this is mostly due to all of the indexes that we have on the table. So let's say that we want to reduce the number of write requests this query is doing. So in order to do that, we can just run our redundant index detection script.
And just to remind users, how did you get all this data on storage read request? Did you run explain with a bunch of like options? Could you just show them?
Right. So to get this output, I ran explain analyze dist on my insert query, and that's how I could see how many storage requests and all of that stuff.
Yeah.
Okay, so now let's run our redundant index detection script and see what it says. Okay, so it told us that there are 5 indexes that are redundant. And it's pretty much all the ones that we expected. So we have this email index where there's already a unique index. We have first name when we already have first name, last name. There's the hash index when we have the ascending index. There's the partial index when we already have the non-partial index, with a warning saying that you might want to keep the partial index. And then the last one is the timestamp updated at index when we already have updated at user ID.
Yeah, it's cool that it's calling out which one is the likely redundant one, which one is the existing one on the left side of this output. And then like the partial index one is worth double clicking on, if I can take a minute or so on that. The viewers, please notice that it gives a warning that the redundant index is the partial index, but the existing one is not. But essentially, there's a trade-off here, right? On the one hand, one index is saying, please index only the rows where the phone number is not null, right? So that may actually be a better thing to do than indexing all the phone numbers, because maybe you have a situation where 90% of the records or the data set in your table does not have a valid phone number. It's a null phone number, right? But you also most likely your app doesn't want to look up rows by the null phone number. It is only interested in looking up records by valid phone number. So in that case, actually the partial index might be the better one to keep, because on the index maintenance side, you're only having to maintain the index for the small number of rows that actually have a valid phone number, and not bother with maintaining the index for the ones where the phone number is null. So yeah.
Yeah, exactly. So now let's say that we decided that we don't want any of these indexes. So let's just drop all of them.
All the ones or the redundant ones?
Sorry, just the redundant ones.
Okay.
We want to keep the rest of the indexes.
Okay.
So, okay, what I did was I just dropped all of the redundant indexes. And then now let's try running our insert query again and seeing if the number of write requests improved. Okay, so now we can see, because we just dropped 5 indexes, our number of write requests when we do our query went from 11 to 6. So performance improved when we dropped all of our redundant indexes.
Awesome. So yeah. And remember, these 6 storage write requests in a distributed database, they could be going to different nodes, right? So it's quite a lot of like RPC traffic eliminated, and that's why that's the other point Kai made earlier, that a lot of what you heard in this talk is generally equally applicable to other databases, because the fact that if you have a composite index on A comma B, you don't also need an index on A is true in any database. So a lot of the thing is true, but the point he made earlier, that in a distributed database, each index adds even more overhead than a single node database, is what makes this really valuable to spend time on upfront and get rid of unnecessary indexes. There are a few questions also coming in, Kai. So one question is maybe not specific to index, but if a table or an index is dropped, how does the storage reclamation work in Yugabyte?
That's a good question. When the table is dropped, how does the storage reclamation work?
I can take that question if you want. Like if a row is deleted, in a log structured storage engine, it doesn't immediately get deleted. You put a delete marker and you keep multiple versions of rows around for a variety of reasons, because databases do multi-version concurrency control, and because Yugabyte is log structured. So there's this process of compactions that periodically reclaims space, for updated or deleted rows. On the other hand, if an entire index or a table is dropped, then the cleanup is easier. You can just remove all the files from it, right? So by default, I mean, it's not so much whether it's hard or is it deferred or what. We can delete it right away. But there are other capabilities, like if you want to be able to do a rewind past an accidental table drop, right, and be able to go back to a point of the system before you dropped your table. There are other reasons that might cause Yugabyte to keep the table around for some time, and that's basically it. So it's not an algorithmic complexity or anything like that. There's a second question, and Kai, you probably, since you wrote the script, like what is the complexity of the redundant index check algorithm? Is it order n squared or is it more efficient? Good question.
That's a good question. Yeah. So the script is just pure SQL. So the query planner decides what join algorithms to use. So it should be more efficient than O of n squared. But because if you have a lot of indexes, the query planner will choose to do a hash join, let's say, and then it'll be just O of n.
Great. And any, do you have any other closing comments? Any other slides left?
No, so that's it. Thank you for attending my talk.
Yeah, we are did well on time at this time. Just wanted to thank everybody that joined us today. And we'll see you on another episode of the YugabyteDB Friday Tech Talk series. So thank you everyone and have a great day and rest of the weekend. Kai, over to you also for closing comments.
Great. Yeah. Thanks for attending my talk, and please test out the script if you get a chance, and let me know how it goes.
All right. Thank you, everyone.